welcome everyone to the session on invited talks from the SIGGRAPH conference. We'll have 6 great talks in the session. And the first talk will be by Monday Drinkerchuff. He will talk about image features, influence reaction time, a learned probabilistic perceptual model for saccade latency. And to remind everyone, if you have questions, please post them on Slido. I can also bring the mic, but it's easier if you do everything on Slido.
All right, thank you. All right, let's get started. So let's consider a scenario many of you are familiar with. You're driving and the pedestrian appears on the road. A few hundred milliseconds and your reaction time actually significantly impacts the outcome of the situation. As a matter of fact, being able to predict how long your reaction time would be in this scenario would be actually very helpful for avoiding such accidents. In essence, being able to tell whether a pedestrian was able to notice the driver was able to notice the pedestrian is not enough information. We want to know also how quickly we will notice the pedestrian as well. So when it comes to computer graphics, the literature has successfully and extensively measured visual acuity of stimuli, or simply the what is visible part. However, when it comes to how visual content influences a reaction or the how fast is a visible part, there's a lot of work to be done. In many applications, such as assisted driving, as I've shown, AR/VR systems, video games, esports, even healthcare, for example, if you consider like a futuristic AR-assisted surgical operation, for example, the behavioral aspect of how we react to visual stimuli is often more important than the visual quality of the images. Hello, my name is Monday, and that's me. And in this talk, we'll present our work for modeling our reactions and when we perceive images and how we can use it in various applications. So specifically, what I'm going to do is I'm going to present a model for predicting how long it takes an observer to complete a visual task depending on what kind of images we're seeing. So to lay some groundwork, let's first define what we measure as a reaction time. In our work to estimate the reaction time of processing image features, we measure the latency of the onset of a saccade. A saccade is the rapid eye movement humans use to move the gaze between different fixation points. And the onset of this movement is characterized by the acceleration of the gaze location. So it's a very easy and consistent marker that we can use as a measure of reaction time. So in this next video, I'm showing our reaction time clock starts ticking as soon as the target appears on the screen. Within the next few hundred milliseconds, the observer processes the target's visual features. And once the observer has identified the target, they will initiate a saccade towards it, as shown in the animation a little earlier. Our results show that visual features of the target, so how noticeable that object is, influences the latency of the onset of the saccade. So more specifically, prior work in the vision science community suggests that the image features that are highly relevant for image acquisition speed are the contrast of the image, as well as the spatial frequency. These two things make up how sharp the image looks, as well as the retinal eccentricity at which the image appears in your eye's retina. So how far off your center of gaze. Given these variables, our model predicts the probability distribution of saccade onset. So depending on various combinations of these variables, our reaction time might be either slower or faster. In the scope of our work, we only consider these 3 image features, but consider that in general, there are a couple more image features that we do not address. We draw inspiration from prior work, and we use a neurologically inspired framework for reaction time prediction. Within this framework, the process of experiencing an event and reacting to it is modeled as a stochastic random walk. Of course, in our case, the event that this stochastic random walk would model is the appearance of some visual stimuli, and the reaction is the onset of the saccade. So in the next clip I'm about to show, I'll demonstrate what the random walk represents, how it works, and how we can use it to predict reaction times. Intuitively, though, this reaction time, or this random walk measures how likely we are to react to an external event. So in this plot I'm showing right now, our stochastic measure of decision confidence varies over time and is visualized on the y-axis in this figure. At the moment an event begins, at the moment an event happens, the stochastic random walk begins. So over time, our brain analyzes more and more details about the stimulus, and we gain a better idea of what it is. Once we have enough confidence, the saccade will trigger, and due to the random nature of this process, because it's a random walk, the latency of the saccade onset is inconsistent, as you can see in these simulations, and hence produces a probability distribution of reaction times. The nice thing is that the probability density function for the reaction time model results in a closed form solution with two open parameters. Our task now is to basically relate these two open parameters to the features of interest to us, namely the contrast frequency and eccentricity of the images that we see on a display. We ran a user study to collect this relationship and collect real data of what this relationship is, and ran a regression model to find the parameters and fit them to the user study data. Here we present the mean reaction times that our model predicts. We fitted the model using a large data set of over 11,000 individual user saccades, and our results follow closely with intuition. So features that make images harder to see, such as making decreasing the contrast of the image or increasing the spatial frequency, increases the reaction times, as you might expect. To kind of use it in some application, we applied our model to various scenes in the video game Counter-Strike Global Offensive and observed very interesting results. In Counter-Strike, the two teams competing against each other, the Ts and the CTs, have different character models, as you can see here. Therefore, the visibility of these characters vary depending on the background that they appear on top of. We analyzed snapshots of in-game footage from esports matches using our model and estimated that on average, a T will spot a CT model around 3% faster compared to a CT spotting a T model on the map Dust2. So this corresponds to roughly 1 frame difference at 60 FPS, which actually could determine the game's outcome for some professional players. Additionally, we also realized that moving the monitor farther or closer from your eyes could also impact reaction times. When we change the display distance, the visual features of an image change with respect to your retina. So for example, moving the display farther from your eyes makes spatial frequencies higher because they're more denser, and retinal eccentricities lower because they're closer to your gaze location, as illustrated in this animation. So to quantify the effects of changing the display distance, we used our model on the gameplay footage. And these plots I'm showing show the reaction times for processing T and CT models. Our model reports that the fair viewing conditions, so when the reaction times for both CTs and Ts are the same, to be around 65 degrees FOV. Well, meanwhile, the optimal conditions for the two teams are actually different. So if you want to optimize your gameplay, the two teams would ideally move their monitor to a different distance from your eyes. So far, I've just shown computational applications of what we can do with our model. Now I'll present a more rigorous validation study on various types of images that we ran. We asked participants of a user study to complete a go or no-go task. In this task at the beginning, they're presented with an image of one of the following scenes: soccer, esports, and photographic. And after a brief delay, a target or non-target object is added to the scene as shown. If a target object appears, the participants are asked to look at the target as quickly as possible, therefore us measuring a reaction time. Otherwise, they're instructed to maintain their gaze at the center until the end of the trial. So that would be the no-go option of the go or no-go experiment. Throughout the trials, the visibility of the target and non-target object is adjusted in order to induce a deferral or acceleration of the reaction times compared to a control case. With 14 participants in this user study and 5,500 saccades as data points, we managed to apply our model on top of the data and compare our data with our model predictions. We compare the results of our, on the left, we present 3 histograms of the reaction times for the 3 conditions I just mentioned, and as well as the predictions from our probability model. Our model succeeds in predicting the trends of each group reasonably well, and looking at the average change in reaction times compared to the control condition, we see that our model is able to predict those as well. In our second user study, we explore whether our model is applicable for a more complex task featuring both foveal and peripheral targets, so increasing the complexity of the task itself, not the image. And we applied our model, and we show that our results actually also align with the user study that we collected as well. Unfortunately, we'll skip the details of the study, and please refer to the manuscript for more information. In summary, we presented a perceptually based probabilistic model for predicting reaction times when completing visual tasks, and showed various applications that the work could be used in, and finally evaluated our work in validation studies emulating real-world situations. There are many interesting applications where models of human reaction times are useful within the computer graphics space. More broadly, the general direction of studying human behavior and performance as a metric to measure and evaluate computer graphics pipelines is a very interesting research direction that we've explored here. In our work, we demonstrated what applications these behavioral metrics could be useful for, and made one of the first steps towards studying human behavior in the context of computer graphics systems. There's plenty of work to be done in this space, such as investigating how we could apply our simple model, simplistic model, for more complex images and tasks in a principled manner. And while our work has still left many questions unanswered, we hope that our results inspire further work in this general research direction. Thank you.
Thank you very much, Mandy, for the great talk. Do we have questions? So could you imagine this being directly applied to a visualization application? Let's say figuring out where something has changed in a bar chart or how long it takes a user to react?
Sorry, could you repeat the question?
Like a typical visualization application, do you think it could be directly applied if you look at a bar chart and then it's updating how long it takes the user to react to the update, or do they?
Yeah, so something like that. So if you have like a UI update, you might actually be able to essentially calibrate your UI to whatever the reaction time you want it to be. A small caveat is there is a calibration that needs to be done per user because your reaction times might be different than mine, but the trends are the same across users. So like I could say, looking at this object with higher contrast takes around 70% of the time it takes for me to look at this dimmer object. And that would also be true for different individuals. So we can still make like generalized claims about the applicability of this model in order to kind of, for not like visibility's sake, but more so for like more controlled in the sense that you can actually tell how long or how much more longer someone will take to notice objects in their periphery.
Mm-hmm. Great, thank you very much.
Awesome.
Other questions? Or, yes? Okay, I see you. Yeah.
Hello.
Yep.
Nice presentation. I was curious, did you find in your test if there are some eye sickness that could affect your model, like myopia or something like that, that could skew the model somehow?
Yeah, all the visualizations here were in color, but I did that mostly for presentation aesthetics purpose. All the user studies we actually ran were in grayscale, so like eye conditions that disallow you from discriminating from color aren't considered. And also we did only consider people with like normal and corrected to normal vision. So I'm not as familiar with like specific eye conditions. But like there are specific cases where your ability to, for stereo vision, from like other research I've worked on, some people aren't able to distinguish stereo vision. And I think in those situations, you have this, you observe this thing where your reaction times might be affected by how well your eyes converge on the depth. And that might also affect how well you are able to localize and acquire visual targets. So I think it's definitely an interesting and future work to consider.
Okay, we have to move on in terms of time. Thank you very much. That was another question on Slido, if you want to have a look. All right, so the next talk will be Clip Hasso, semantically aware object sketching.
Your phone.
And the presenter will be Arik Shamir from Reichman University.
Of course it won't work when I'm trying both modes. And great. Okay. Thank you very much for the introduction. So my name is Ariel Shamir, and this is a joint work by 3 universities, EPFL, Tel Aviv University, and Reichman University, which is my university. I'm going to name Yael Winker, the first author. She's my PhD student, and obviously she did most of the work I'm going to present. So let me start by some motivation and tell you that abstractions, I believe, are core to any art. Whenever an artist wants to create something, either painting or sculpture, she needs to extract only important parts of what she sees in reality. And more specifically, I'm going to give you an example. This is a series of sketches by Picasso. And you can see that Picasso creates a progressive abstraction of a bull. And as the sketches become more and more abstract, basically Picasso concentrates on the more general features of any bull and goes away from the specific depiction of a specific bull. So this axis that we define is, on the one side, things are a bit more geometric in a sense that they're more related. Okay, they're more close to reality, to this specific bull. And then when you abstract something, it becomes more general, related more to any bull that you can see. So our goal was really to try algorithmically to create sketches and a series of sketches that move from more geometric to more semantic presentations of objects. And so we call this CLIPASO, semantically aware object sketching. And as you can see, even though we're getting more and more abstract, the actual features of the object are preserved, like the long leg of this flamingo or the long neck, even though we have very few strokes to create. And this was created by our algorithm. So we are not the first one to deal with sketches and to try to mimic sketches. There are numerous previous works. And in fact, they were concentrating on these two extremes. So some of them concentrated more on the geometric side, either by extracting the edges from the images, or by asking people to trace the images, or by just asking them to draw from an image. So this is on one side. On the other side, there are some sketch data sets that are actually created by asking people to draw objects, like elephants or other things. But one thing to remember in all these previous works is that they were always trying to mimic specific data sets. So they gathered data set and then they created a learning algorithm that learns from this specific data set. And that means that they are many times limited to a specific style or abstraction. And also, many times they're limited to specific categories that they find in this data set. So our motivation or our approach is really to create something that will be, in a sense, unsupervised. It's not really unsupervised because we are leaning on previously trained models. So in a sense, it's zero-shot learning. But in a sense, we don't need any data set to create our sketches. And it can apply to any objects that you want. So let's discuss our approach. It leans on 3 main components. So the first thing is, how do we define a sketch? So when we define a sketch, we just use a set of strokes. In our case, these are Bezier curves. And the more strokes you use, the less abstract the sketch is, right? So when you move to more abstract, you just reduce the number of strokes, and that creates a more abstract representation of your sketch. The second component that we were leaning on is an optimization algorithm. And this optimization algorithm actually takes our strokes and rasterizes them into an image. Now, we're using that in order to then use the image and compare it to the original image that we got as an input. And we're not just using a simple rasterizer, we're using what is called a differentiable rasterizer, because we want to then change the positions of the strokes, and that means that we're using gradient descent from the difference between the two images. And I'm going to go into details in a minute. And the last component that we were using is really the clip-based loss. So the loss that we're using is based on a pre-trained network, which is called CLIP. So CLIP is a neural network that was pre-trained on over 400 million image and text pairs in a manner that will create what is called a shared latent space where you can map both images and text into that space. And the idea or the training was using what is called contrastive learning. Basically, it takes two pairs that are found together on the internet and tries to bring their representation closer to each other and more closer to pairs that are not matching. And this was pre-trained by previous work. And the fact that it was actually using both text and images created this semantic space that we wanted to use. Now, this network is actually very good and very useful for a wide range of applications like image descriptions and semantic segmentation and other application. And it's also very useful for various types of inputs. So because it was trained both on images and on text, it can actually be very robust to the representation that you're using, including also sketches. So here's an overview of our method. In general, we get as an input an image. We initialize the position of the sketches somehow, and then we run an optimization procedure that changes the parameters of those strokes so it will fit better the image that we got as an input. So let me get a little bit into the details. I'm going to talk about the initialization in a minute, so let's concentrate on the optimization procedure. So as I said, the learned parameters of the sketch is really the positions of the control points of the Béziers that we're representing each stroke. And then after we have those positions, we run them through the differentiable rasterizer, and what we get is an image, some image. Now we take both this image and the original image we got as input, and we pass them through CLIP, which is the pre-trained network that I was describing. And we get some latent representation of both the sketch and the image. And in fact, what we want is we want the two to be very close in latent space. That's where we get the semantics from, right? So both the sketch and the image should be close to each other in the latent space. And then if they're not close, what we do is we then propagate the gradient, which is the difference between the two things, through the networks all the way through to the parameters, and we change the parameters. And then we run again. We run them forward again, rasterize, and create a better representation of the sketch. And then back propagate again, and again, and again, and gradually we get the sketch that we want. Now, let's talk a little bit about the loss functions. So the first term that we used is, as I said, the difference between the latent representations of the sketch on one hand and the image on the other hand. And we were using cosine distance between those two. And basically that says that I want the semantic meaning of the sketch and the image to be similar in clip space. And that brings those two very close together. But in fact, if we just use this term, what we get is images similar to this. And as you can see here, the sketch did get some horse features, but it didn't resemble the specific horse that I wanted. And that's why our goal was really to do both, to have this semantic representation of a horse, but also to resemble this specific horse. So we added another geometric term, and using, in fact, again, clip, but not the embedding representation in the end, but more close or more middle representations of the network. So we use the fourth layer and the features in the fourth layer, and we're using, again, L2 distance between those two. So the embedding of the image and the embedding of the sketch, but now not at the end, just in the middle. And basically, this is similar to other neural networks. As you get closer to the input, the features are being more geometric and less semantic. So together, we get this loss that combines these two terms together. And if we combine them together, we get a better representation, both semantically and geometrically. Just one word about the initialization. So in fact, if you look at this error loss function, this is highly non-convex function. So it means that you have many, many solutions, possible solution. And the initialization actually affects the final stage, the final solution that you get. And some initialization get better results than the others. So you can compare here two initializations, and we believe that the right one is better than the left one. Now, we found out that if we actually initialize the strokes in a more semantic places where there are salient regions for the specific object, in this case the dog, the face, the tail, and so on, you get better results in the end. So in order to initialize our strokes, what we do is we extract some semantic and salient map of our input. We add on top of that some edge detection, and that's where we initialize the positions of our strokes, and that actually helps us to get a much better result in the end. So let's see some examples. What you can see here are some optimizations as they are running and slowly converging to the solution. And as you can see, when you go from left to right, you have a higher level of abstraction when we reduce the number of strokes. Now, our algorithm, as I said, is a zero shot. So basically, it doesn't depend on any input and any training data. And so it actually can abstract any image that you want or any object that you want. It doesn't depend on any specific class. And as you can see, some non-traditional classes we can also abstract and create. Okay. Now, on top of that, obviously, because we're using vector graphics, we can apply any stylization to the strokes themselves, and we can create these types of images, which are more, sketch-based or pencil-based or oil or painting and so on. And of course, everyone likes cats, so we were gathering random, 100 cats from the internet, and we were running our algorithm to all those cats, and we got these results just so you see that we didn't actually pick the best ones. This is a random representation. Some of them are better than the others, of course. But one thing I want to remind you is we do have this initialization, which is in effect random. So in fact, the sampling-based approach also allows us to create various outputs as we change the initialization. And this is very similar to humans, right? So whenever you sketch something, when you sketch it again, you don't get exactly the same sketch. You get a different sketch. So this is what we do. And in fact, on each object, we were trying the results that you've seen. We were trying 3 times, and we took the one that has the smallest loss function in the end, and this is what we present. But obviously, you can try more, and that gives you variability. Let's talk a little bit about limitations. So the first one is we're actually not using the background. So whenever you have a background, we are just masking it out because we're just sketching the object. And if you do have a background, you get some of these results which are not really the object, but more the scene. And so this is part of the future work. Also, the strokes are optimized all together. So it doesn't actually resemble how people draw, because they draw non-sequentially. They start with the first one, and then the second one, and the third one. So we can actually do that, but the results I'm showing you is really when they're optimized simultaneously. And the third thing is that the number of strokes is not a really good way of thinking about abstraction in terms of perception. So in this example, you can see 2 examples of level of details, and in a sense, I think that they resemble and they look in the same level of abstraction. But in fact, when you think about the number of strokes, we were using twice more strokes in the top image than the bottom image. And so we were trying to think of a better measure of what is a real abstraction level, better than the number of strokes. Okay, so to conclude, I really thank you for listening. And if you have any questions, you can ask. Also, if you scan this, you can also try yourself. We have a website where you can upload the image and you can create sketches and play with our algorithm and code as well. So thank you very much.
Okay, great. Thank you very much for the great talk. So we have a question in your work. How do you generate saliency maps?
Again, sorry?
How do you generate saliency maps?
How do I, what?
How do you, saliency maps?
Well, the saliency map that we were using is, again, it's previous work that actually uses also CLIP as the network to find what is more salient. But you can use any saliency algorithm, so this is not something that is special to it.
And another question, how do you compare this approach from cycle GANs or style transfer?
Well, so again, cycle GAN and style transfer, they need data sets in order to actually create these types of things. So we are, in a sense, zero-shot learning. So it's
great. Thank you very much again. Thank you.
I think he has one or two.
So you were talking about the number of strokes, a bunch of, I guess I was curious if there's limitations on the length of the strokes, because I noticed that some of those sketches kind of took advantage of making one continuous stroke that went some larger distance to kind of capture more of the image. And so I guess I was just curious, like, what is the relationship between length and number?
Right, so we actually have no limitation. So we, as you noticed, we start actually with the strokes very short, and then basically the optimization opens them up according to how much space they have and how many strokes there are and so on. So you're right that when you have less strokes, they tend to be longer, but we have no no limitations on the.
So I guess what prevents the algorithm from using just one continuous stroke for an insanely long amount of time to capture a lot of detail?
So two things. One is you have to remember these are specific cubic Béziers, so they can't turn too much, right? So that's one thing. The second thing is whenever it has more strokes, it basically tends to use them in order to cover whatever is in the image. So this is the idea.
Thank you. Sorry for in terms of time, we have to move on.
Yeah,
thank you very much.
Me afterwards.
Thank you.
Thank you very much. And I think
thank you very much again. So the next presentation, thank you. The next presentation will be online.
We are going to present our work, Joint Neuroface Retrieval and Compression for Energy and Computation Efficient Holography on the Edge. I'm Yujie Wang, a PhD student from Shandong University. This work is in collaboration with Pranish Chakravarshila from Princeton University, Qi Sun from New York University, and Bao Chen, my PhD advisor from Peking University. Recent advances in several areas have made VR headsets lightweight and ubiquitous. The applications supported on VR devices bring us a compelling experience by providing us with a sense of immersion. For example, VR gaming is one of the most compelling applications which provide us with a first-person perspective of gaming actions. In the near future, we anticipate this immersive technology will bring us endless possibilities. Lightweight VR and AR headsets require that devices are not equipped with powerful computational units. Simultaneously, similar to our phones, wearable display headsets have a limited battery budget. Thus, computation-intensive applications are not suitable for operating such headsets for as long as a day. On the other hand, current VR and AR headsets are bulky. In contrast, holography shows the potential to achieve compact form factor displays. Besides, holographic near-eye displays are also capable of providing us with continuous focal control at correct accommodation codes. While hologram rendering demands heavy computing, cloud-based rendering potentially elevates this problem. For cloud rendering and streaming, we have two possible solutions. The first one is to transmit the desired content to the client and carry the hologram computation on the edge devices. However, most of the holographic face retrieval methods are computation intensive. This results in high computation and energy costs, which is not suitable. Another solution is to shift the computation totally to the cloud server. Simply put, the edge devices just download the pre-computed holograms. Unfortunately, due to the immature coding techniques for holograms, the data volumes incurred in this approach are very large. This results in high streaming latency considering the limited available internet bandwidth. To understand the problem better, let's have a look at how face-only holographic displays work. A face-only hologram is displayed on a special light modulator, which modulates the phase of the incident light. The modulated light then propagates to a distance and is observed by human eyes. And the resulting interference pattern is the desired intensity image. Computing appropriate phase patterns to generate the target intensity image is the core problem of computer-generated holography. Note that the quality of phase patterns directly affects the quality of reconstructed images. As mentioned before, most of high-quality phase retrieval methods are computation-intensive. Besides, as for the compression of holograms, the existing codecs such as JPEG are unfortunately not efficient in reducing the hologram data volume. As the statistics of natural images and face holograms are very different, thus the prevalent compression codecs are not very effective on hologram comprehension. For example, using 2 bits per pixel is sufficient to encode a natural image, while noticeable artifacts can be seen within the reconstructed image, even with using more than 9 bits per pixel to encode a hologram. Thus, to guarantee the reconstruction quality for holograms, using current compression codecs unfortunately needs to consume much more bits. In this work, we propose a joint neural phase retrieval and compression framework for cloud-based holographic display rendering. Our framework asymmetrically distributes the computation between cloud servers and edge devices and optimizes the compression efficiency in an end-to-end manner. We propose that the cloud servers conduct hologram computation and compression. Specifically, for a target image, we use an initial phase predictor to initialize a phase distribution at the target plane. Then the complex wave field at the target plane is numerically propagated to the epsilon plane. We then use an encoder to encode the complex wave field into a latent space. Note that the elements within latent space are floating point numbers, and directly transmitting the floating numbers requires significantly large number of bits. Therefore, we introduce a latent field compression module into our pipeline. Specifically, we allocate fewer bits to represent elements that frequently occur and assign more bits to those elements that occur rarely. To this end, we model the distribution of latent space for efficient encoding. Specifically, we integrate a hyperencoder and decoder network to estimate the distribution of the elements within the latent space. Then, we quantize the elements to make them more discretized. Finally, we utilize entropy coding to code the latent space into a bit stream. We then transmit the coded bit stream to edge devices. After receiving the bit stream, edge devices decode the transmitted data into a face-only hologram. Now I will elaborate on the decoding process on edge devices. During the decoding process, we first utilize the entropy decoding to recover the latent space. We then feed the latent space to a phase decoder to produce the hologram. Once the hologram is decoded, we then reconstruct the target image. You may notice that the latent space distribution is also needed, but it cannot be directly transmitted due to its large data volume. Instead, we duplicate and deploy the hyperdecoder to edge devices. Parallelly, we code the intermediate latent space to another bit stream and transmit it to edge devices. one stream, we can then decode it on edge devices and reproduce the distribution parameters. Finally, we finish the decoding process on edge devices. Now, let me introduce the training procedure of our framework. Overall, to stabilize the training, we train the proposed framework in 2 stages. In the first stage, we train a subnetwork formed without the compression-related modules. In this stage, we treat the neural modules with the reconstruction loss, which is calculated between the reconstructed image at the target input. We treat the subnetwork until convergence and incorporate the compression-related modules for the second stage training. We encourage the framework to use fieldbits to store the information. We add supervisions on the number of bits within the bit streams. Now we finish the training and let's have a look at the performance of our framework. Here we show a few results. It can be seen that our framework is able to produce significantly better results when bit rate is as low as 5, at which JPEG codec produces visibly degraded images. For JPEG codec with quality 95, although the bit rate is higher than 3 times of that for our method, the reconstruction quality is still visibly worse than the ones produced by our method. Besides, we also present more numerical analysis in the paper, which shows that the proposed framework shows great gains over alternative solutions, which is helpful to lower the transmission costs. Please refer to our paper for more details. We also evaluate the energy consumption of decoding modules within our framework. It can be seen that compared with running the trained HoloNet on edge devices, the computation and energy consumption for decoding modules in our framework are significantly lower. We note that with an increasing number of users, energy savings obtained with our framework pronounces more. Additionally, we also investigate the scalability of our framework to holographic video compression. Here we conduct comparisons with a straightforward alternative of using popular H.264 video codec to compress holograms generated by HoloNet, which is another state-of-the-art phase retrieval method. It can be seen that our framework produces fewer artifacts while using a low bit rate. Finally, we evaluate our framework on a real hardware prototype display and show several results as captured by a camera. The experimental results show that the quality of the reconstructed images by our method using just 5 bits is comparable to those of the other 2 state-of-the-art methods, which consumes at least 3 times more bits per pixel. This further demonstrates the effectiveness of our framework. In summary, we propose the first framework device for cloud-based holographic displaying scenarios in the future. Using an end-to-end framework with coupling hologram generation and compression, the transmission efficiency is highly improved by reducing the number of bits for coding holograms. By asymmetrically distributing the computation between cloud servers and edge devices, our framework significantly reduces the energy consumption for edge devices. That's all for this work. Thank you.
Thank you very much. Do we have questions? Hello. Can you hear me?
Yeah, I can hear you.
Other questions? So I have one question. You targeted, I guess, natural-looking scenes. What about sketches or illustrations or vector graphics or this kind of, would that work with this encoding?
Oh, sorry. Can you explain the question more?
If you use a scene that looks more like a sketch or an illustration instead of a natural scene, would the encoding work well?
Yeah, I think in our training data, all of the images are natural scene looking. Yeah. Actually, I didn't get the problem. I didn't get the question well.
Okay, there's one question on Slido. Does the network speed affect the result of the hologram? Or does your method require high network speed?
Okay, you are saying how we can achieve a high speed for calculation and compression and decoding?
I guess it means if you require a high-speed network connection.
Yeah. Okay, I see. Because they introduce compression-related modules to reduce the number of bits required for coding the hologram. So we think that we can reduce the load for the network bandwidth.
Okay.
Already.
Okay, thank you. All right, thank you very much. We have to move on. Thank you very much again.
Thanks.
The next presentation is also online by Nick Sharp.
This is Spelunking the Deep, guaranteed queries on neural implicit surfaces via range analysis, and I'm Nick Sharp. Computing with 3D data is all about finding the right representation, from point clouds to voxel grids, tent meshes and triangle meshes, to spline, CSG trees, and implicits, and more. There are many different representations with various strengths and weaknesses. Today, we're going to look at a particularly promising kind of implicit surface representation and see some new computational tools that help us really unlock its power. The basic idea of implicit surfaces is to represent a shape via the level set of some function. This function takes 3D XYZ coordinates as input and produces a real number as output. And by convention, we say that the points where this function outputs a negative value are inside the shape. In neural implicit surfaces, this function is a neural network. These offer benefits from gradient-based optimization to excellent compression properties, latent and data-driven manipulation, and more. And more generally, these are part of a class of techniques called neural fields, which have been widely studied lately for the particular case of surfaces, and also more broadly for encoding visual and scientific data. Now remember, we have all of these representations for 3D data, and because there are many different tasks we want to apply them to, we've seen the emergence of a really wide range of different, sometimes quite complicated methods. For instance, optimizing 3D reconstruction with a triangle mesh might require a whole suite of remeshing tools, hierarchical solvers, heuristics, and so on. These neural implicit representations are exciting because for many of these tasks, they end up just being simple gradient-based descent on the weights of the neural network. And this is really appealing. This works so well that it's useful and being widely applied, even in cases where there's not really any machine learning going on per se. We just use this neural network as a function space to solve a single problem of interest. So not only do these neural implicit representations often easy optimization of many different objectives and many tasks by just minimizing some loss function, but they also adaptively represent varying complexity without explicit choices of discretization. They're easy to integrate with the machine learning toolbox when we do want to do so. Although there are some downsides. They require a great deal more computation in terms of just the number of floating point operations. And also, this is the real kicker, it can be difficult to make use of these representations for downstream tasks. And this last one is the one we're going to focus on today. So given all of these cases where we might want to use a neural implicit representation of a shape, how do we query that representation? For instance, how do we take a ray that we want to cast in space and find where it intersects the surface? Or given two of these neural implicit shapes, how do we test whether or not they overlap each other? The way this has been tackled in the past is by using what's called sign distance functions, or SDFs, where not only does our implicit function define the surface, but also its magnitude gives the distance to the surface. If you actually have a high quality, accurate sign distance function, then doing a lot of these geometric queries isn't so bad. But being limited to sign distance functions has a lot of downsides in the neural context. First, neural networks only ever approximately model SDFs, leading to robustness problems. And more deeply, this property only holds at the end of training, so you can't use it in loss functions, which you would need to apply at the beginning of training. And also many computational tasks are just more naturally phrased on models for the surface other than signed distance functions. So all of this is to say is that we want to do queries and geometric operations on neural implicit surfaces which are not necessarily signed distance functions. And this is the main task that we try to tackle in this work. We're not going to introduce any new architectures or any new loss functions or anything like that. We're going to give you new tools to compute with the neural networks you already have, which have already been fitted to all of these interesting tasks, and we'll provide a set of techniques that makes no particular assumptions about the function encoded by the neural network. So if we're going to analyze these kind of shape representations, we need a new tool at our disposal. Our tool is a decades-old technique from numerical computing called range analysis. Range analysis takes a function and a range of inputs to that function that we're interested in and computes bounds on the output of that function over the range. The most basic kind of range analysis is called interval arithmetic, where we take each scalar value in a computational expression and replace it with lower and upper bounds on the value over that range of inputs. Then, as we perform operations, we can push these bounds forward until we eventually get a bound on the output of our computation. So for instance, here are what some of these update rules look like if we're tracking bounds for upper and lower values on a scalar in interval arithmetic. So this is like an automatic function transformation. You can think of interval arithmetic or range analysis more broadly as being kind of like forward mode auto-differentiation. But instead of automatically computing derivatives, we're going to automatically compute bounds on functions. This is the foothold that lets us start analyzing these implicit functions. We can take a region of space, do a forward evaluation of a network with range analysis, and get at a bound on the value of our neural net over that region. So for instance, if this bound is greater than 0, then it tells us that that entire region is certainly strictly outside the shape, no matter how crazy the function encoded by a neural network might be. So this lets us start building up geometric queries. However, it's not quite that easy in our case, because although the bounds from any kind of range analysis are always guaranteed to be valid bounds, in the sense that they really do contain the function output on the region of interest, they might not necessarily be tight bounds, in the sense that they could be much looser bounds than the set of values the function actually spans. And indeed, if we naively apply this interval arithmetic technique to neural networks, we get bounds that are so loose they're totally useless, due to cancellation that happens inside the linear layers. Fortunately, if we dig a bit deeper, there are more advanced forms of range analysis beyond interval arithmetic. And in particular, we make use of affine arithmetic. You can think of affine arithmetic as being like a first-order upgrade of interval arithmetic, where we track linearizations of error quantities for intermediate values inside of the network. This is still a fully automatic arithmetic scheme, but even better, it has the property that it automatically preserves bounds under affine operations, like the linear layers in our network. In the end, these affine arithmetic operations provide a very effective trade-off between reasonably tight bounds on our function and modest computational overhead. A big technical component of this work was doing an empirical study to find just the right version of affine arithmetic, which is effective on these kind of neural networks that we use to represent implicit surfaces. So we condense all of this down into a subroutine, which takes a neural network representing some implicit surface and a bounded region of inputs that we're interested in, and tells us that the network output on that region is either strictly positive, strictly negative, or not necessarily either. We implement this routine, as well as the high-level geometric queries to come, in a machine learning framework, along with some tricks for efficient vectorized GPU implementations. The most standard query that we want to build using this range analysis is, as I mentioned before, casting a ray in space and testing where they intersect the shape, most often used to generate images when rendering an implicit surface. Here's a visualization of this happening. These blue figures that I show are all implicit neural network, which I've fit with a variety of different activations and objective functions. In this case, it's an occupancy function, not a signed distance function. If we want to march this ray forward in space to cast it into the surface, we can first analyze this interval shown here. And sure enough, range analysis tells us that it's strictly outside the shape, so we can march forward. If we test this interval, well, maybe our range analysis is a little bit too pessimistic with its bounds, so we don't see that it's outside of shape. But if we try a smaller interval, we're good to go, and we can continue marching and marching and marching until eventually this ray converges to the shape. With this, we're able to render this image like I show here, and the plot on the right shows the number of steps that this ray casting procedure takes. We can also push this a step further and use spatial analyses of 3D volumes to push an entire frustum of rays forward at once by looking at bundles of pixels in image space. This spatial acceleration hierarchically accelerates the procedure for high-resolution data. Now remember, here we're working with implicit functions which do not necessarily have any special structure. Without our method, the only recourse would be to cast rays using small fixed-size steps. But taking large steps leads to errors, like you see on the left, whereas taking very small steps would be prohibitively expensive. And our approach is better than either. To really put this range analysis to work, we can use it to construct spatial acceleration hierarchies like KD trees over our implicit surfaces. In these KD trees, each cell represents a region of 3D space, and we use range analysis to bound the function in that region as strictly inside or outside the surface. If a cell straddles the surface, or range analysis is ambiguous, we recurse into a smaller cell. Here's a visualization of one of these trees. The yellow cells are all nodes of the KD tree classified as strictly outside the implicit shape. The purple cells are ambiguous. We would need to keep refining to classify them. It's interesting to notice that the ReLU activation leads to planes of uncertainty shooting out into space, although if we refined farther, we would indeed classify these nodes just like the others. This data structure makes it easy to implement a whole range of efficient volumetric queries, all following standard procedures in geometry processing, but now we're able to do them on neural implicit surfaces. A first common operation is sampling points on or near the surface, which shows up often in geometric loss functions. Here, rather than uniformly rejection sampling from all of space, we can sample only from the nodes of this KD tree which are near the surface. This yields dramatic speedups, and importantly, it still yields the exact same result. It's not an approximation strategy, it's just an acceleration. Similarly, we can also perform fast mesh extraction by running the marching cube algorithm only on the leaves of the KD tree and skipping any nodes which we know to be empty. Once again, this gives order of magnitude speed up at high resolution while still provably producing the exact same result as running dense marching cubes. We can also come back to this question of intersection and test whether two shapes overlap by building a combined KD tree where we discard any node which is strictly outside of either shape. The result is either a guarantee that the two shapes do not overlap or some point in their intersection. And one more of these, we can use the KD tree to perform closest point queries, where here on the right, each black point is a query point in space, and the red point is the corresponding nearest point on the neural implicit level set, found by searching the spatial KD tree. We can do this either explicitly, building the whole tree ahead of time, or implicitly by lazily constructing only the subset of the tree we need. So wrapping all of this up, we saw how we can use range analysis to bound the output of an implicit neural network in a region of space. And this enables us to perform geometric queries and build spatial hierarchies. To be clear, this is still slower than the fastest SDF-based methods, but that's because it's a much more general method which applies even to randomly initialized networks and offers provable guarantees of accuracy. Also, in this work, we focus mainly on simple MLP-like architectures, but the core idea could generalize to almost any neural network architecture. There's a lot to do. With that, I'll wrap up. See the link here for the paper, code, and more. Thanks.
Thank you very much. Do you have questions for Nick? Okay, so maybe I've got one. Could you imagine this applying directly to volume rendering, like full volume rendering, not just implicit surfaces?
Yeah, absolutely. Hopefully you can hear me here. Hi, everyone. A lot of the same techniques would be useful for volumes because you want to be able to quickly skip regions of space or maybe sample more densely in regions of space that are interesting or have a rapidly changing function. So this gives you a way of, no matter what your volumetric data might be, as long as you can apply these range analysis and interval arithmetic techniques to it, then you get a handle on the function. You can sample it only where you need to and hopefully implement more efficient volumetric renders.
Okay, thank you very much. More questions? Okay, if not, we have to move on. We are a bit out of time. Thank you very much again, Nick. Great presentation. The next talk will be by Kirill Brod.
To pose estimating at Kirill, and I'm presenting sketch to pose estimating a 3D character pose from a bitmap sketch. Artists often capture human poses via sketches, from detailed character sketches to quick and rough gesture drawings. These drawings are then often used as a reference while manually posing a 3D character in an animation software to create an animation prototype. The manual posing step requires special training, is tedious and time-consuming. We propose to sidestep this tedious process completely. We introduce the first system that algorithmically computes a 3D pose given a skinned 3D character model in a bind pose and a single raster sketch in a different pose. Our system supports a variety of sketches. We thus enable animators to create a draft of the animation immediately and automatically from the storyboard they draw. Previous research looked into an option to use stick figures, lines of action, and silhouettes. Those inputs are ambiguous even for humans. Besmeltsev reconstructs a character pose from a clean vector drawing, which is extremely hard to get automatically. Instead, we focus on natural bitmap sketches. There are alternative works solving this problem by splitting the 3D pose inference into two stages. They first infer 2D joint positions and then optimize the human model to match those positions. We are inspired by this line of work. All previous works in computer vision assume that the photographed human is a projection of a 3D human with correct proportions. For the task of posing a 3D character from a sketch, however, this is not the case. Sketches are imprecise and cannot be interpreted as projections. So our task is to reconstruct the 3D pose that the artist wants despite these inaccuracies. This is a hard task because sketches are imprecise, so proportions, perspective, and foreshortening are all distorted. So, even for a human, it's trivial to tell that those legs are more or less parallel to the screen. Formally, they are foreshortened. If we naively trust the drawn 2D bone lengths, the 3D pose will look fine from the same view as the image, but will look too foreshortened from the side view. Probably not what you expect. We can easily compute the 2D joint positions. However, we cannot trust them because of distortions. We focus our analysis on three key elements of the drawing: foreshortening, tangents, and self-contacts. Artists often exaggerate foreshortening, so they draw body parts shorter than they should be. Our job is to undo this transformation. Angles are one of the key elements of the drawing, creating pose expressivity and dynamism. Humans are more sensitive to changes in angles rather than in the absolute positions, so it's more important to preserve tangents. Contacts between different body parts are key element of many poses. Here, a person is drawn touching their hip. We expect that to be preserved on the final reconstruction. Finally, we observe that humans expect a somewhat natural pose. So, we predict three key elements of character drawing: 2D bone tangents, body part contacts, and bone foreshortening. First, we predict 2D tangents and preserve them from this original view. Second, we predict image space self-contacts and try to preserve them. Here again, contact between arm and hip. Finally, we explicitly model and undo the distortions of the depicted bone foreshortening. Let's take a look at the algorithm overview. We split our system into 4 separate components. We first predict 2D joint positions on the character sketch, which are used in the initial rough alignment of a 3D human model. We then predict screen space contact regions, which we map onto the roughly aligned 3D model, resulting in a set of contact vertices in red. We compensate for inaccuracies in depicting bone lengths in foreshortening transformation stage. Finally, we leverage all these components in an optimization framework, yielding the final 3D pose. For our first key element, initial alignment, we use the state-of-the-art framework exemplar fine-tuning to produce an initial alignment. For our second key element, self-contacts, we first predict heat map areas of potential contacts in the image space. To know which body parts are participating, we first separate different contacts, and then we map each contact region onto the mesh vertices. Perhaps the most non-trivial component of our system is calculation of foreshortening. We predict the correct angles of each bone with the screen by transforming the drawn foreshortening of each bone. In order to compute this transformation, we compare the distribution of the drawn foreshortening with the distribution of what realistic foreshortening for bones should be. We minimize the Earth mover's distance between those two distributions. You see here our resulting transformation traces the depicted foreshortening for small and large angles but reduces it for non-extreme angles. Depicted bone lengths control the angles between bones in the screen like these ones on the side view. Finally, we use all these elements in the optimization that gives us the 3D pose. We start with a roughly aligned pose and minimize the following energy. We aim to preserve angles by enforcing 3D bones to be parallel to the 2D drawn ones. We use the transformed bone foreshortening to guide the target length of each bone's projections. We preserve relative positions of mesh vertices and self-contacts. Finally, we add the regularity term, enforcing symmetry and parallelism of the final pose. As a framework, we use exemplar fine-tuning. Here are a few results. We can see that the poses capture the essence of the drawn pose, even though the proportions of the depicted character are different from the green character. In conclusion, we introduce a system that algorithmically computes a complete 3D pose given a single raster sketch of the character. Our system supports a variety of sketches. Our framework is robust to the input bitmap gesture drawing with noise and distorted proportions. We thus enable animators to create a draft of the animation immediately and automatically from the storyboard they draw. Thank you for your attention.
Thank you very much. Thank you very much. Okay. Okay, then let's move on. Thank you very much again. Let's move to the last paper, which is being presented by Samara Ren and Uday Kusupati.
Welcome to the presentation for our paper Umbrella Meshes.
We are PhD students from the Geometry Computing Lab at EPFL.
I'm Samara.
I'm Uday.
Umbrella meshes are a new type of elastic mechanisms that deploy into doubly curved surface-like structures. Deployable structures are fascinating mechanisms that can transition between multiple configurations. They find applications in diverse fields including medical devices, aerospace engineering, and architecture. Let's examine two of these structures more closely.
The Hoberman sphere is composed of identical rigid linkage elements and expands greatly in volume as it opens. Eggshells are assemblies of elastic beams that buckle and deform into curved surfaces when expanded. The Hoberman sphere has an especially compact initial state, but its rigid elements limit the space of deployed shapes. We seek to combine the best of both systems by assembling vertical linkage units composed of beams that elastically deform. Our result is a class of structures that we call umbrella meshes. They feature a compact volumetric rest state that deploys into a doubly curved surface-like structure. In the highlighted view, you can see how the initially straight beams deform and the whole structure is bending active. To understand how the structure works, let's start with the unit cell. Our unit cell is inspired by the mechanism that deploys an umbrella. It consists of two plates connected by three scissor linkages. Bringing the plates together expands the unit in plane. If we assemble several identical unit cells, they too expand uniformly in plane. We can determine this expansion factor using kinematics. Here, m is the side length of the plates and h is the height of the unit cell. We note that the expansion factor increases linearly with the unit cell height. Therefore, if we connect two cells of different heights, they will expand to cover different areas. As we connect more unit cells of differing heights, something interesting happens. The incompatibility of their expansions eventually forces the structure to buckle and elastically deform into a curved 3D shape. Different height distributions in the compact state produce different equilibrium shapes. This raises the question, how can we design the height distribution to reproduce a specific target surface? For this, we first must understand how to simulate the deployment of an umbrella mesh.
Our simulation employs the popular discrete elastic rods model to represent the deformable beams. We then couple the rods together using a generic hinge joints model implemented by an efficient nonlinear change of variables. Finally, to model actuation forces, we introduce a virtual linear actuator that drives the distance between the top and bottom plates to a target value. For more details on our simulation model and numerical methods, please see our paper and the longer version of the talk. Our deployment simulation is quite fast, as seen in this real-time simulation recording. With our simulation framework in place, we can now tackle the inverse design problem.
Our design optimization aims to compute a structure that deploys close to the target surface, has low strain in its beams, and minimizes separation forces in the deployed state so that the top and bottom plates do not pull apart. The first step of our design optimization seeks the 2D footprint of the compact state and a good initialization of the cell heights. We do this using geometric insight. Notice that each individual unit expands isotropically, and this pointwise uniform expansion is the defining property of a conformal map. The connection to conformal maps gives insights into how the heights of an umbrella mesh control the intrinsic curvature of the deployed surface. Specifically, our kinematic analysis, combined with a well-known equation from conformal geometry, directly relates the Gaussian curvature to the height distribution. More importantly, this conformal mapping analogy also leads to a fast and robust algorithm for design initialization that forms the first step of our computational design pipeline. Our algorithm begins with the user's target surface, which is conformally flattened to the plane. We then superimpose a regular equilateral triangle grid over the parametric domain, sample the conformal scale factors on this grid, and use them to convert each triangle into an umbrella unit. Deploying the resulting initial structure typically gets close to the target surface, but the fit is imperfect. To improve the design, we pose an optimization of the height variables. Our design optimization minimizes the sum of objective terms that each promotes one of the design goals introduced earlier. At each iteration of the optimization, we must compute the equilibrium of the current design and update its parameters using sensitivity analysis. Here is a time-lapse of the optimization, which significantly improves the surface approximation compared to the initial design. We'd finally like to mention an important feature of our design parameterization related to symmetry breaking.
If we optimize only a single height variable per unit cell, we encounter a problem during deployment. While the structure is sometimes deployed properly, you can see the left half of the structure pops in the wrong direction this time. Without external guidance, this structure does not reliably deploy into the correct shape. The underlying problem is that a single height design parameterization produces a compact state with vertical symmetry. It is able to encode the Gaussian curvature of the surface, but not the extrinsic curvature. One of the key advantages of our material system is that its structural thickness enables us to break this symmetry to ensure automatic deployment to the correct shape, with no external guidance. We do this by independently controlling the top and bottom heights of each unit. The asymmetric structure found with this expanded design space reliably deploys to the desired target shape. The enhanced design parameterization also improves the surface approximation fidelity, especially for near-developable surfaces. As shown by the last example, separate control of the top and bottom structure heights is crucial to encode mean curvature and ensure reliable deployment. At the same time, several considerations restrict the introduction of further design freedom. First, we want the compact state to be free of residual stress for easy fabrication. Second, we wish to employ identical triangle plates to support mass production. Consequently, we use the top and bottom height variables for each umbrella units as our design parameters. Since umbrella meshes have zero residual stress in their compact states by construction, they can be 3D printed as a single piece with no assembly required. Note how the deploy structure can greatly exceed the built volume of the 3D printer. For larger models, CNC milling can be used. We mill the compliant joints onto a pair of umbrella arms and mill the triangle plates separately. We then assemble these pieces together to get a single unit cell, and combine unit cells of differing heights to build an umbrella mesh. Another key advantage of umbrella meshes is their theoretically unlimited in-plane scale factors. This has important implications on the design space. To illustrate this point, here's a sequence of umbrella meshes that cover a larger and larger portion of the sphere. Doing so requires progressively greater scale factors that exceed the limits of previous auxiliary materials. We built and deployed the largest example pictured here. We observed that the stiffness of umbrella meshes can be controlled by adjusting structural depths. The stiffness and corresponding weakest deformation modes are found by solving a generalized eigenvalue problem. As visualized here, increasing the plate separations increases stiffness, and the structure deforms less. Interestingly, our experiments have shown that umbrella meshes tend to be bistable. Plotting the elastic energy endured by the structure during deployment reveals an energy barrier between the initial and deployed states. Here's a case study coupling an umbrella mesh with elastic fabrics. We envision this type of structure serving as a stadium roof. We hope to explore such architectural designs and many new applications in the future. Thank you for listening.
Thank you very much. Questions?
Hello, hi, can you hear me?
Yes.
Hi, so my question is, what is the largest size of this mesh that you have implemented, and do you know at what point the weight of the components of the structure itself might start becoming an issue in the model?
So for all our experiments in the paper, we did not explicitly consider gravity, given the material we're using. The elastic energy is much higher than the gravity. The elastic stress due to the strain in the beams is much higher. But one of the large models that we have implemented is the large subset of the sphere that we have shown in one of the slides. And it still withholds well in presence of gravity. But for larger architectural models, yes, absolutely, we need to consider gravity. And yes, that is still something we need to incorporate.
Thank you. Yeah, great work. Thanks.
Thank you. Do we have more questions? Can you say how challenging it was to manufacture the 3D printed joints? Is that a problem, or is it?
So the 3D printing was actually the easiest way to make umbrella meshes with a support-free SLS printer. The hemispherical shape that we showed, after it comes out of the printer, we can right away deploy it. For the larger models, the milling approach we took has an assembly after fabrication, and the assembly usually takes a couple of hours for models with around 50 to 100 umbrellas. And in particular, the deployment actuation or the spacing, the insertion of the spacers might also take a few more minutes after the assembly. But the 3D printed models are ready to go out of the printer.
Okay, thank you very much. So if there are no more immediate questions, we are over time. Thank you very much to all the speakers again, and thank you to all of you for attending.